Welcome to the Explainer. Today we're going to crack a classic coding problem. And what I love about this one is that the obvious solution is actually a trap. It's a puzzle designed to make you ditch that brute force mindset and find a way more elegant mathematical path to the answer.
So picture this. You've got the numbers 1, 2, 3, and 4. You know there are 24 different ways to arrange them. Now, if you were to list all 24 of those arrangements out in perfect order, how could you possibly find the 17th one without actually writing out the entire list? That's the challenge we're going to solve.
All right, first things first, let's make sure we're all on the same page about what the problem is really asking. The key phrase here is lexicographical order. Now, that sounds super fancy, but it's really just dictionary order. Think about it. With the numbers 1, 2, and 3, you'd start with all the permutations that begin with 1, then all the ones that begin with 2, and so on, just like you'd find words in a dictionary.
So our mission, should we choose to accept it, is pretty clear. We're given a number of elements, n, and a position, k, and our job is to pinpoint the exact single permutation that lives at that kth spot in the list.
So let's say you're in a coding interview. What's the very first thing that pops into your head? Probably the most straightforward, direct way to solve it, right? And that's the brute force approach. I mean, it is exactly what it sounds like. You just tell the computer, generate every single possible arrangement. Throw them all in a big list, sort that list, and then just pluck out the one at position K. Easy enough, right? Well, not so fast. That simple, easy-sounding approach has a massive, hidden problem, one that will bring the whole thing grinding to a halt. You see, the number of permutations for n items is something called n factorial. This means the time your algorithm takes doesn't just grow, it explodes. This is what we call a factorial time complexity, and in the coding world, that is a gigantic red flag. Just to give you a little perspective, if n is only 12, you're already looking at almost 500 million permutations. Trying to generate and then sort a list that huge? Yeah, no, your computer's not going to be happy about that. It's just wildly impractical. And this is that moment. The moment in the interview where the interviewer leans back and says, okay, that's way too slow. You need to find a better way. This is the real test. So if brute force is a dead end, we need a new path. Let's talk about the optimal solution. Instead of trying to build this mountain of data, we're just going to use a little bit of math to jump straight to the answer. Here is the big aha moment. We don't have to generate anything. We can actually construct or build the permutation we want, one digit at a time. If we can figure out the first digit, then the second, then the third, we can build our answer directly without any of the extra work.
And this is where the pattern reveals itself. For n equals 4, those 24 permutations aren't just a random jumble. They're actually neatly organized into blocks. You've got a block of 6 permutations that all start with 1, another block of 6 that start with 2, and so on. Understanding these blocks, that's the secret sauce. Okay, theory's cool, but let's make this real. We're going to go back to our original example. N equals 4, k equals 17, and we're going to use this block method to find the answer, step by step. First, a quick but really important bit of housekeeping. You know programmers love to count from 0. It just makes all the math work out a lot cleaner. So instead of looking for the 17th item, we're actually going to look for the item at index 16. So from now on, k is 16. All right, let's do this. Step 1, finding that first digit. We have our numbers available, 1, 2, 3, and 4. And we already figured out that the permutations are grouped into blocks of 3 factorial, which is 6. So to find our first digit, all we do is take our target index, 16, and divide it by the block size, 6. The answer is 2, with a remainder. That 2 tells us which block we need to be in. So we look at our list of numbers, 1, 2, 3, 4, and we find the number at index 2. And that number is 3. That's our first digit. And the remainder from that division? It was 4. That becomes our new target index for the next step. So we've locked in the number 3. We can take it out of our list of possibilities. We're now left with 1, 2, and 4. And guess what? We're just going to do the exact same process all over again. Now, since we only have 3 numbers left, our block size gets smaller. It's now 2 factorial, which is just 2. We take our new target index 4 and divide it by our new block size, 2. The result is 2. So we look at our remaining numbers, 1, 2, 4, and grab the one at index 2. That's the number 4. Bam, there's our second digit. And this time, the remainder is 0,
which will be our target for the next steps. And we just repeat this until we're out of numbers. With our target index at 0, we'll always just pick the first available number, which is 1. That just leaves the number 2. And there you have it, 3, 4, 1, 2. We built it piece by piece without ever having to look at a single other permutation. You can see the whole process laid out right here. At every step, the logic is exactly the same. You divide your target index k by the current block size. That gives you the index of your next digit. And then the remainder from that division becomes your new k. It's just a clean, predictable, and beautiful loop. So, we went from a brute force method that just completely grinds to a halt to this really clever mathematical approach. So what's the bottom line? What does that actually mean for performance? Oh, the difference is just staggering. It is night and day. We've gone from that impossible factorial time complexity to O(n)². And while n² isn't perfect, it's so much more efficient. It's the difference between a solution that only works in theory and one that actually works in the real world.
And that really brings us to the big takeaway here. This problem, it's not just about permutations. It's about a whole way of thinking. So often, the most powerful solution isn't about writing more code or more complicated code. It's about taking a step back to find that elegant mathematical insight that's been hiding just beneath the surface the whole time. It really makes you wonder, doesn't it? What other problems out there seem impossible until you find the right shortcut?